9.3. The last section we're doing in Chapter 9. There's technically 4 sections in Chapter 9, but we are not doing the 4th section. So we will end with measures of regression and prediction intervals. I am not going to lie to you. This is going to be the worst section. Some of it's more challenging, but overall it's not even so much that it's hard that makes it the worst, but that looking at the formulas are intimidating, and we kind of go back to what we were doing like way back in the first 9 weeks, where we were making columns and rows and squaring things and subtracting things and adding things together. So it's just a little bit tedious in comparison. But we're going to just do this in 2 days. So this would be a section that if we were in class together, we could probably finish in 1 class period. But since we're doing this online and with video lessons, I don't want to overwhelm you with what could very well be a 45-minute video of me going through this section. So we're going to just do it in 2 days. You can either watch half of it today and half the next class, or you can watch it all today and just do the homework the next class. That's kind of up to you. I just do it whatever's going to make you the most successful. So we're going to start with measures of regression and prediction intervals. So before we can really look at the two measures in correlation and regression, coefficient of determination and standard error estimate, we have to understand our types of variation with the regression line. And I didn't put this in the notes because it was too tedious to try to get in here, but in your book on page 498, there is a graph right underneath the first little couple of paragraphs with the heading that kind of show you what some of these things are that may help you kind of visualize it a little bit more. So totally your call if you want to look at it or not. But when we start talking about these variations, total variation, explained variation, unexplained variation, what you first have to do is you have to find deviations. So total deviation, explained deviation, unexplained deviation. And we do that for each data pair, each ordered pair in our set. So after you find all of your deviations, that's when you can find your total variation, your explained variation, and your unexplained variation, which are the 3 main things that we have to understand first. So total variation about a regression line is the sum of the squares of the differences between the y value of each ordered pair and the mean of the total variation. So basically, what we would do is we would say, okay, here's my y value from the ordered pair. I'm going to take that and I'm going to find the mean of all my y values and I'm going to subtract them. You're going to do that for every data pair. Every y value that you have, you're going to subtract from the mean. Then you're going to take all those differences and you're going to square each one of those differences, and then you're just going to add them all up. So it's just another one of those column things. Your explained variation is the sum of the squares of the differences between each predicted y value and the mean. So instead of using the y value that you're given in your data pair, you would say, okay, if my x value is this, my regression line or my line of best fit, if I plug this x value in, it's going to give me my predicted y value. You're going to take those predicted y values, subtract your the mean of your y's, square all of those differences, add all of those up. That's your explained variation. Your unexplained variation, that's the sum of your squares of the differences between the y value in each ordered pair and your corresponding predicted y value. So what y value do you actually have in your data versus what y value your regression line or line of best fit says that you should have. So you subtract all those, you're going to square each of those, and then you're going to add up all your squares to find that sum. So I'll be honest, you'll use your unexplained variation a lot more than the other two. It's just kind of how it is. But the sum of your explained and the sum of your unexplained variations have to equal your total variation every time. So in section 1, we found our correlation coefficient, which was just R. The square of that coefficient is called the coefficient of determination. So that's one of the main things in this section that we have to talk about. It's just R squared. Okay, so correlation coefficient is R. That was section 1. Coefficient of determination is R squared. Now you have a formula that you can use to find your coefficient of determination. It's just the ratio of your explained variation over your total variation. So if you know what your explained variation is and you know what your total variation is, you can divide them, and that's going to be your R squared or your coefficient of determination. If you already know what your R value is, let's say that you have a correlation coefficient of 0.9. To find your R squared, you're just going to square 0.9. So 0.9 squared gives you 0.810. And when you interpret that, you got to remember, everything in stats tends to come down to the interpretation. So when we're interpreting this 0.810, what that's telling us is that 81% of that variation in y can be explained. Okay, so it can be explained between whatever the relationship is between x and y. And then that remaining 19% is unexplained. And due to other factors that could be sampling error, coincidence, some lurking unknown variables, things like that. So when you're finding R squared, whatever R squared is, that's the percentage of variation that can be explained based on whatever the relationship is between your x and y values. The rest of that percentage is unexplainable variation. Okay, so when we look at number 1, the correlation coefficient for the Old Faithful data that we did in section 1 was 0.979. We want to find the coefficient of determination, and then we want to know, what does this tell us about the explained variation, about the regression line, and the unexplained variation. So remember, we know what R is. So to find R squared, we just have to square R. So 0.979 squared is going to give me about 0.958. So what does that tell me about the explained variation of the data in our regression line? So 95.8% of the data variation can be explained by the relationship of, and I believe Old Faithful's X and Y was the length or duration of the eruption and the time between. So that's the 95.8, that should be 95.8% of our data can be explained based on the relationship between our X and Y variables, our duration of interruption and the time between eruptions. And then the unexplained variation would just be that remaining percentage. So if 95.8% can be explained, then 4.2% is unexplained variation. Now, the hardest that problems like this is going to get is if you aren't given your R value first, or you don't have your variation values. The hardest it's going to get is that you might have to find R before you can find R squared. As long as you remember how to interpret, you should be good. Okay, your standard error of estimate, SE, is the standard deviation of the observed Y values about the predicted Y value for a given X value. So Y sub I is your observed value, and then your predicted value is always the Y sub I hat. So that formula is just going to be the square root of the sum of your observed Y value minus your predicted Y value squared divided by n minus 2. So n is the number of pairs of data. And then the closer together your observed values are to the predicted values, the smaller your standard deviation or standard error of estimates is going to be. So if you get really small numbers, but your Y sub I and Y sub I hat values are really close together, then you're going to have a smaller standard deviation. If your predicted values and your observed values are really far apart, you're going to have a much larger standard deviation or standard error. So just kind of be paying attention to, okay, do I have a lot of room in between those two values, or are they closer together? And that should give you a gauge on if you should have a bigger or smaller standard deviation. So when you're finding the standard error of estimate, the first thing you're going to do is you're going to make a table that includes the 5 column headings: X sub I, Y sub I, Y sub I hat, Y sub I minus Y sub I hat, and Y sub I minus Y sub I hat squared. So your X sub I and your Y sub I, that should just be whatever the ordered pairs in your data are. So that's just your data from your ordered pairs. The Y sub I hat, that's your predicted Y value. So that's going to be what you would get from plugging your X value into a regression line equation or a line of best fit equation and deciding what Y value you should have for that X value. And then Y sub I minus Y sub I hat is going to be taking this column with your data set Y values and this column with your predicted Y values and subtracting them. And then your last column is taking that column previous and just squaring each of those. You're going to get a total. So you're going to add all of those data values up and find that sum. That sum is also your unexplained variation. So that sum that we're using to find our standard error of estimate is our unexplained variation. So we're going to make those tables. We're going to make those calculations. We're going to put our x's into our equation to find the predicted y values. we're going to subtract the data y values and the predicted y values, and then we're going to square them. We're going to add them all up, take that total, put it into our equation, and find that standard error of estimate. So when we look at number 2, a researcher collects the data shown and concludes that there is a significant relationship between the amount of radio advertising time in minutes per week and the weekly sales of a product in hundreds of dollars. Find the standard error of estimate. Use the regression line y hat equals 1.405x plus 7.311. So I'm going to do a lot of the work for you to save time and space. So our x values, that would be like x sub I in our formulas, and the weekly sales would be like y sub I. So I'm going to just extend that table so that I can continue to add my other columns. So in order to find my predicted values, my y sub I hat, I'm going to take each of these x values and plug it in for x in that y hat equation. So I'm going to do 1.405 times 15, and I'm going to add 7.311, and that's going to give me 28.386. And then I'm going to plug in 20 for x and do 20 times 1.405 and add the 7.311, and I'm going to get 35.441. And I'm just going to continue doing that for each of those x values. So those are all of my predicted y values. The next thing I'm going to do is I'm going to subtract the y values that I was given and my predicted y values. So I'm going to fill in that next. So I'm doing 26 minus 28.386, which is going to give me negative 2.386, 32 minus 35.441 is negative 3.441. And I'm just going to continue doing that throughout the rest of those values. So 38 minus 35.441, 56 minus 49.461, and so on. And then my last column is going to be to take, this column previous and to square each of those. Now my suggestion would be to wait and round these decimals until the very end so that you have a more precise answer. But that is essentially up to you. I would at least make sure you keep 3 decimals, preferably more, but at least 3. So I'm just taking that number in the column before and squaring it. So negative 2.386 squared is going to give me 5.692996. Remember, that last column should not have any negative numbers because any number squared is always a positive number. So negative 3.441 squared is 11.840481. 2.559 squared, 6.548481. And I'm just going to continue down squaring those numbers. So once you have all those squared, you want to add that entire last column up and find the sum of your data. Remember that sum is also our unexplained variation. So it's going to give us 231.998938. And now we just have to plug into our standard error of estimate formula. So S sub E is the square root of this sum that we found. So 231.998938 divided by n minus 2. So we have 1, 2, 3, 4, 5, 6, 7, 8 data pairs. So we're going to divide it by 8 minus 2, or 6. And when we work all of that out, we end up with about 6.22. Now, remember, our weekly sales was in hundreds of dollars. So 26 was actually 2,600. 32 was 3,200. So when we look at this standard error, that 6.22 is in hundreds of dollars. So it's really $622. So the standard error of estimate of weekly sales for ad time is $622. Okay, so prediction intervals. This is going to feel very much like confidence intervals back from chapter 6. And they are very similar, but they're also a little bit different. So with prediction intervals, two variables have a bivariate normal distribution when for any fixed values of x, the corresponding y values are normally distributed, and for any fixed values of y, corresponding x values are normally distributed. So the key there being normally distributed. I don't want you to get too worked up about that definition because regression lines are assumed to have that bivariate normal distribution. So you don't have to really worry about finding that or making sure that it has that because we tend to just assume that they do have it. So this formula is going to be the rougher one. Given a linear regression line or equation, y hat equals mx plus b, and x sub o, a specific value of x bar, a C prediction interval for y is y hat minus e less than y hat plus e. So this is literally exactly like we had in chapter 6 with our confidence intervals. It's just that we would do means, proportions, standard deviation, variation. We didn't do y hat. So that's the difference now. So to find E, we are going to find a critical value T sub C. So T sub C is going to come from the T table times our standard error of estimate times the square root of 1 plus 1 over n plus n times x sub o minus x bar squared divided by n times the sum of x squared minus the sum of x all squared. So your point estimate is y hat, your margin of error is e, the probability that the prediction interval contains y is c, or your level of confidence, assuming that the estimation process is repeated a large number of times. So we are doing a confidence interval. It's just using regression lines instead of our normal point estimates. Instead of a mean, a variation, a standard deviation, it's just using a regression line. So when we construct a prediction interval for y for a specific value of x, we're going to identify the number n pairs of data and the degree of freedom, which is going to be n minus 2 this time. So make sure you make a note of that, because normally our degree of freedom is n minus 1. It's n minus 2 for these. We're going to use the regression equation and the given x values to find the point estimate. We're going to find the critical value, TC, that corresponds to the given level of confidence, C. So that's going to come straight from our t-table. We're going to find the standard error of estimate, S sub E. We're going to find our margin of error, and then we're going to find the left and right endpoints and form the prediction interval. All right, so in number 3, the regression line for gross domestic products and carbon dioxide emissions data is y hat equals 166.900x plus 115.725. Construct a 95% prediction interval for the carbon dioxide emissions when the gross domestic product is 4 trillion. What can you conclude? So this 4 trillion, that's your specific x value. So in this case, that's going to be your x sub O. Now, to save us some time, I went ahead and gave you some of these values already. So we had a data set that had 10 pairs of data. When we found our given y values minus the predicted y values squared, we found the sum of that. We found that to be 108,563.70605. The sum of all our x's is 24.6, and the sum of our x squareds is 79.68. So n is 10, which means our degree of freedom is going to be 8 because it's n minus 2 or 10 minus 2. We also are going to need x bar. So x bar, remember, is our mean, the sum of our x's divided by the total data pairs. Well, the sum of our x's was 24.6, and we had 10 data pairs. So x bar is going to be 2.46. So now the first thing I'm going to do is I'm going to find my critical value, and I'm going to find my standard estimate of error. Standard error of estimate. So my critical value, that TC value, if you go to your t-table, you are going to use that first row that says level of confidence, and we're going to go over to 0.95 because we want 95%, and we're going to go down to our degree of freedom of 8, which is going to give me a critical value of 2.306. And I want to find that S sub E value. So it's the square root of my y sub, the sum of my y sub I minus y sub I hat squared, which is that 108,563.70605 divided by n minus 2, which is 8. And I'm going to get 116.492. So what I have to know to be able to find my interval is what my y hat value is for my x value. So I have my equation. So I'm going to find my y hat value for that 4 trillion, that x sub O. So I'm going to plug 4 in for x. Oops. So I'm going to multiply 166.9 times 4 and add my 115.725, which is going to give me 783.325. I'm going to use this y hat value for the actual interval. Okay, so I kind of have all the nuts and bolts pieces of this now. So now I can find my margin of error. So to find that margin of error, remember we're taking our critical value, which was 2.306. I'm multiplying it by my standard error of estimate, which was 116.492. And then I've got this terrible looking square root. So 1 plus 1 over n, or 1 over 10, plus n times x sub o, which was 4, minus x bar, which was 2.46 squared, divided by n times the sum of x squared, which was 79.68, minus the sum of x squared. So when you're working that out in your calculator, I would not nearly try to do any of this in one step. What I would do is I would say, okay, 4 minus 2.46 is 1.54. Square that, multiply it by 10, and then divide it by that bottom part. That you can do all at once. Just make sure you put it in parentheses. So 10 times that 79.68 minus your 24.6 squared, and then add your 1 over 10 and your 1, and take the square root of that number after you do everything on the inside. And then once you take that square root, you're multiplying it by your 116.492 and your 2.306. So you should get about 297.168 for that e-value. So to find your actual interval, you're taking the y hat value that we found, so that's 783.325. We're subtracting the 297.168, and we're going to add that 297.168. And we're just writing that final interval. So if we subtract the 297.168, we got about 486.157. And if we add it, 1080.493. So these are tedious, I know. So if you need me, if you need help, if it's during our class time, get on the Zoom call. If it's after, email me, request a Google Meet, whatever you need to do. Just make sure you get a hold of me so that you can figure out what you are unsure of.